Hello and welcome to the optimized Java 8 stream refactoring tool demonstration. Here is our GitHub page where the tool can be downloaded and used. It is available on our Ponder Lab organization. It's called Optimized Java 8 Stream Refactoring and is available for public download. The source is also available, and we also have some instructions here on how to use the tool as well as install it. It is an Eclipse plugin. It can be installed in two different ways via the update site here or by dragging this icon from the Eclipse Marketplace onto a running Eclipse workspace. So actually, let's go over to an Eclipse workspace that I have pre-installed the plugin on. And here I have an example of some Java 8 streams. First off, we have an unordered stream of widgets here. Widgets are simply things that have a color and weight. And this is a hash set that holds unordered widgets. So hash sets are intrinsically unordered. We're going to store it in a collection here. And what we want to do now is use streams to sort these widgets by weight, which is what we do here. So I declare a stream from this collection. This is actually going to give me a sequential stream as opposed to a parallel one where the operations are, in this case, are executed serially. To do the sorting, I'm going to call this intermediate operation called sorted. This also happens to be what's called a stateful intermediate operation because it may require multiple passes on the data or some buffering on there. We're going to pass a parameter to this sorted operation. This returns a comparator, and we're going to give it a method reference get weight, which just means to sort them by weight in an non-decreasing order. Finally, we're going to reduce the stream via what's called a terminal operation. In this case, there's a special reduction called the collect, and we give it what's called a collector. In this case, this is going to collect to a list, and notice that matches the declare type that I have here that I'm storing in sorted widgets. Okay, so let's switch things up a little bit. We're going to also have another collection called ordered widgets, and let's pretend that we populate the collection somehow. Notice that it's an array list. Array lists, unlike hash sets, actually maintain ordering. And we're going to instantiate that appropriately. All right, so this code is going to collect widget weights over 43.2 units, whatever that is, into a set, and it's going to do it in parallel. So this time we're going to work on the ordered widgets collection. We're going to call, instead of the stream method, we're going to call the parallel stream method, which again is an intermediate operation. We're going to map each widget to its weight, right, which gives us a double. And then we're going to filter by a threshold value here. And then finally, we're going to collect that into a set. This is a set collector. And this is all going to happen in parallel. And it's going to be stored in this heavyweight widget set. And again, notice that the declare type here is compatible with that of what this collector returns. Okay, next up, we're going to sequentially skip the first 1,000 widgets and collect the remaining into a list. So we'll start with the ordered widgets here. We'll do this serially this time, skipping the first 1,000 elements and finally collecting them into a list. Next up, we'll collect the first green widgets into a list. So again, we'll start with the ordered widgets, and then serially we're going to filter each of the widgets for a particular color. So we'll get only the green ones. And we're going to unorder that and also then limit to the first 5. Finally, we'll collect them into a list, into this variable called first green widget list. All right, next we're going to collect distinct widgets into a set. So we'll start with the unordered widgets, and now we're going to call sequentially, right, the stream method here, which creates a new stream. And by the way, these intermediate operations for the most part, return new streams. This one actually flips a field in the receiver stream to run it in parallel when the terminal operation is called. So in parallel, we're going to map each of the widgets to its weight, right? This is called a method reference here. And we're going to find the distinct weights and collect those into a tree set this time. So tree sets are actually a little bit different than hash sets in that they actually maintain element ordering. So we're going to store that into distinct widget weight set here. Okay, next up, we're going to collect distinct widget colors into a hash set this time. So we're going to do this in parallel, again, starting with the ordered widgets. We'll map each of the widgets to its color, We'll get the distinct colors via this stateful intermediate operation distinct. By contrast, by the way, map is not a stateful intermediate operation. It's just a normal intermediate operation because it only needs to pass through the data once. Distinct, you can imagine, may need to do that multiple times. Finally, we're going to call another form of the collect reduction here. This time, we're going to actually give it a little bit more detail. We're not going to give it a collector, but rather we're going to give it the specifics of what we want to store. So we want to use a hash set, and this is called a constructor reference to the constructor for hash sets. So the ordering will not be maintained. And then we just give it some operations here. We're going to say that, okay, add, right, is a method reference to the method that adds elements to the set, and this is for merging. So this method will merge two sets together. Okay, so our last example here is going to be a little bit different. We're going to collect widget colors matching a particular regex, which is right here, and we're going to collect those into an array list called results. We are not going to do it via a collection operation this time, so let's have a look. So we're going to start with the ordered widgets. We're going to do this sequentially. And we're going to map each color, each widget to its color, rather. And then we're going to take that, each color, which actually is like an enum, we're going to map that to a string, a representation. We'll filter the string colors, the strings of colors based on the regular expression that I defined earlier. And now we're going to do a reduction that's called for each. So that means that for each of these elements that have reached this point, we are going to actually manually add them to this result set here. And by the way, we're going to do this sequentially by the stream operation. Okay, so here's our example. It's a little bit involved, but just to show you the different kinds of scenarios and the way that the refactoring tool works. So I'm going to get out of full screen here. And there's a couple different ways we can invoke the refactoring. One way is to right-click on our project that we would like to work on. Right-click that and then click or select rather refactor. And we'll just move down to optimize streams. Okay, so we have a wizard that pops up here. I'm just going to minimize this a little bit to make it a little bit less larger and a little bit more focused. Okay, so we have some options here for the refactoring. These are mainly due to entry point selection. So there's different ways you can define entry points with this refactoring. One way is actually to have it automatically discover entry points. For example, you may want to just consider all main methods as entry points. If you have a GUI application, that may not work out so well. So we actually do have Java FX entry points as well as some other ones. Alternatively, you can also define explicitly your entry points via an annotation library, which is available on our GitHub webpage. Finally, there is a k-value parameter. We use a k-CFA algorithm to construct our call graph. The minimum value you need for this is 2 because we are analyzing stream client code. So this particular example, 2 is just fine, but depending on which APIs you call, you may need to increase this parameter. Luckily, our tool has a heuristic for finding out if client code is not being analyzed. In other words, that the k-value is too small. So we'll give you a precondition failure there so you can go back and adjust that accordingly. Okay, so we'll click next here. We're taking these parameters. Okay, so we can see here that our refactoring is ended. And before we go on to the transformation, we have a report of some problems that are found. So let's start with the first one. So here the error is that no stateful intermediate operations exist within the streams pipeline. I'll make this a little bit larger so we can see it. Streams pipeline is just a sequence of operations that get queued up prior to the terminal operation. All this error is really saying, it's not really an error, but it's just saying that there's no optimizations available for this stream. So it's already in parallel, right, via this call. And furthermore, there's nothing that can hinder in this particular stream pipeline the parallel execution of these operations. So for example, there are no stateful intermediate operations in this pipeline. Moreover, this lambda expression, right, which is passed to the filter operation, doesn't have any side effects on the heap. So it's good to go. There's nothing more that the refactoring can do here. Okay, so in contrast, we do have some other ones here. So ordering of the result produced by a terminal operation must be preserved. So in this case, we have a stream that is currently sequential. So the refactoring is trying to make it in parallel. However, the problem is that there is a stateful intermediate operation here. And to do this, we would want to unorder the stream. So this is actually an ordered stream. And when we run things in parallel, actually maintaining the ordering of the stream is cumbersome to the runtime. So we would want to unorder the stream prior to running it in parallel, but we can't do that because we need to maintain element ordering. And you can see here that this actually lists the two lists, right? All lists in Java actually maintain ordering. So there's no way we can unorder that. So you're actually better off staying sequential there. Otherwise, you'll incur some overhead. Okay, so the last one here is that this is actually associated with a behavioral parameter that may contain side effects. And that certainly is the case here. So we have a heap access right here to this result, and it's unsynchronized. So if we change this stream to now run in parallel, there could run a chance of a race condition. Okay, so those are the errors. Let's see actually what it can do. So for this one, for the sorted widgets by weight, you can see here that it's been parallelized, right? So we've actually changed the call to stream from stream to parallel stream. And the reason that happened is because of the unordered widgets. So the collection is unordered. Henceforth, the parallel processing doesn't need to maintain the ordering. So in this case, it's advantageous to parallelize the stream. So let's go to the next one. Okay, so this one was also parallelized. So this is to collect the first green widgets into a list. And we can see that there are no side effects, right, in the lambda expression here. And also it's unordered, right? So we started actually with an ordered stream, right? But we called this unordered method on it. So for the same reason, right, we don't have as much overhead to run this in parallel, this pipeline. So we go ahead and refactor it. Okay, next one over. So the collect distinct widgets into widget weights into a set. This one was parallel, but actually you can see that it has been removed in the refactored version. And let's see why. So it's an ordered set, ordered widgets rather, right? So ordering needs to be maintained. However, that can be problematic in pipelines that run parallel, especially if they have a stateful intermediate operation, right, that has multiple passes in the data. So, and it can't unorder this one, right, because we're actually, the target collection here is actually a tree set, right? So tree sets maintain ordering. So if we were to unorder that, we actually could alter semantics. So that one actually goes from parallel to sequential. And finally, we have the collect distinct widgets colors into a hash set. So hash sets do not maintain element ordering. And you can see here that we're actually running this in parallel. We do have a stateful intermediate operation, right, distinct here. But the key insight here is that we are collecting this into a hash set, which does not maintain ordering. So we start off maintaining ordering, but we actually don't wind up using it. So it's actually like a wasted maintenance that's going on here. So what the refactoring does is actually calls the unordered intermediate operation here to deorder the stream prior to the stateful intermediate operation so that its execution in parallel actually can have less overhead. Okay, so that's all the refactorings for this example. Let's click Finish. And that makes the source code changes. And we actually have undo functionality as well. I'll make this a little bit bigger here. And if we like, we can actually go to the edit menu here and say undo optimize streams, and everything goes back to normal.